Okay, welcome to lecture. Get started here in just a sec. We're off to the next chapter, to be chapter 9. And again, these notes should be up there if you need them. All right. Okay, so we're going to talk about the liquid state. We're going to talk about how molecules and molecules basically interact with each other, and how that interaction basically will affect things like boiling point, freezing point, that sort of interaction that occurs between one molecule and another. And let's get started then. All right, so we're going to talk about intermolecular forces here, and there's sort of a difference between sort of two types of forces that we'll talk about. And the two major sort of types of forces, one is what is sometimes referred to as an intramolecular force. And an intramolecular force means basically within the molecule, it's the force to basically hold one individual sort of molecule or compound together. So for example, in water, if we look at just one water molecule by itself, the covalent bonding that occurs between the oxygen and the hydrogen, the sharing of electrons, and the same deal on this side between the oxygen and the hydrogen, that is what is known as obviously covalent bonding, and that's intramolecular force. So the individual bonds between the hydrogen and the oxygen on each side there are intramolecular forces. Things like electrostatic attraction in ionic compounds, the positive negative attraction, that is what holds that particular compound together, is known as an intramolecular force. What we'll mainly be focusing on is intermolecular forces in this chapter. And really, intermolecular forces happen when you get, say, two water molecules together, for example, or more. And it's the force that will hold one entire water molecule together with another entire water molecule. And that's what's known basically as intermolecular forces. And that's, again, like I said, what we'll sort of be focusing in on here in this chapter. And when we talk about sort of strengths, if you could try to sort of imagine the one that is the stronger of the two between intramolecular forces and intermolecular forces, as we will see, is intramolecular forces are stronger. And we actually know that from a very simple example, which is kind of the one that we have on the screen here. We know when we take something like water in the liquid state and we start to heat it, what ends up happening is this bond breaks first. The bond between one water molecule and another water molecule. And obviously it would go into something like steam that you see like when you're boiling water, right, to make pasta and stuff like that, all the steam's coming up. And we know that that means that the intermolecular force is weaker than the intramolecular force. Because if it was opposite, and you did that same thing, you started heating, say, water, liquid water up, and if the intramolecular force was actually weaker, what would happen is the bond between the oxygen and the hydrogens and every single water molecule would start to break. And if that happened, you would make a lot of hydrogen gas and oxygen gas, which probably wouldn't allow you to get to your pasta at that point, and that would not be so good. So we know that this doesn't happen, right? When we heat it under normal conditions, what ends up happening is actually that weaker intermolecular force is the one that breaks, and we actually get water molecules that come out. And again, if the intramolecular force was weaker, then we would have a situation, like I said, sort of like alphabet soup. Everybody would fall apart, and you wouldn't have any sort of molecules that are together. So let's talk a little bit about these intermolecular forces. Again, the intermolecular forces, as I mentioned, and as I drew on that last slide there, again, are the forces that basically hold one entire sort of molecule together with another. And as we'll see in pretty much all these sort of examples, if you will, or all the ways that intermolecular forces really work, is they work on a really basic concept, and this concept we talked a lot about in this class is that opposites attract. So basically how intermolecular forces work is the attraction between a positive side of something in a molecule and a negative side in the other. So it's that opposites attract that occur, and we get that attractive force that holds one molecule together. No matter sort of what the situation is, that's sort of the ultimate way that pretty much all these intermolecular forces basically work, is there's some type of positive side and there's some type of negative side that come together. So the attractive forces between those molecules is what holds them together, and it's responsible for sort of the condensed states of liquid and matter. It's also responsible for things like melting point temperatures, freezing point, boiling point temperatures. Again, the stronger that intermolecular force is, the larger the higher the boiling point would be, for example, because the stronger that force is that holds, say, this molecule together with this molecule, the more energy you got to put in there to try to break it. And the more energy that you would have to put in there to break it means that it usually relates to a higher boiling point. So we're going to talk about sort of relative strength of these different types of intermolecular forces. And again, sort of the ones that have that kind of really stronger intermolecular force, usually we see a much higher boiling point when we look at it. And it's really important in terms of boiling points, because what happens at the boiling point, as you hopefully should be aware of, is at the boiling point, right? That's where we go from liquid to gas. So at that transition, when we go from liquid to gas, you have to put in there a lot of energy to do that, because you have to get everybody 100% apart from each other and completely apart. And as I mentioned earlier and kind of drew the picture as well, this is very different than intramolecular forces. Again, that intramolecular forces are those forces that are within the actual molecule itself that holds it together. And as we just talked about, it is much, much, much stronger than any intermolecular force that you come across. So, something, again, that sort of falls into this category in terms of intramolecular forces. These are things, again, like electrostatic attraction, ionic bonding, basically. Also covalent bonding. Again, these are sort of intramolecular force that holds the individual molecule together, and again, much, much stronger. So what we're talking about here, first off, is again, all these examples that we're going to be seeing here, just to remind everybody, these are all intermolecular forces. So all these examples that we're going to talk about at this point on here are all going to be focusing in on intermolecular forces. Again, are forces that are between two individual molecules that hold them together. So the first type of intermolecular force is dipole-dipole forces, or dipole-dipole interaction. And you might remember dipole from when we talked about bonding. Dipoles are things that happen in polar molecules. And basically, if you remember, if you have a polar molecule, for example, like water, it has what is known as a dipole moment, right? That kind of big arrow. which means there's a negative side of the molecule. There's also a positive side of the molecule. And ultimately, basically, that's what it means is something has a dipole moment and it's polar. It has a fixed side of the molecule that always is going to be positive and one side that's always going to be negative. And again, that's the result of unequal sharing of electrons as a whole in that molecule. And that provides really the basis for how polar molecules kind of interact with each other. A lot of polar molecules will interact with each other through this dipole-dipole interaction. And much like the picture sort of shows, basically what you got going on is you have one polar molecule that has a positive and negative side. And when it gets in contact with another polar molecule, which also has a positive and negative side, the negative side of one polar molecule will be attracted to the positive side of another. And that is where that interaction is going to come. And that is where that intermolecular force is going to come. It's going to hold, again, one polar molecule together with another. Now, when we get, we sometimes think about it as just kind of two molecules come together. But obviously, if we have a certain amount of a substance, like if you had a glass of water, in that glass of water, obviously, it's not just, two water molecules, right? There's a ton of water molecules in there. So what happens, obviously, is when these guys sort of align themselves in a solid state, what they try to do is align themselves in such a way that it sort of maximizes that attractive forces and also tries to minimize how close those like forces are to each other. So that negative and negative, they try to kind of move around until they sort of get to a place where they really, as best they can, maximize the positive negative attraction, but minimize, obviously, positives being near each other, or negative sides of molecules being near each other. As you know, right, things with the same charge don't like to be near each other. So if you get two positive sides of a molecule kind of getting near each other, they will sort of repel each other and kind of go in the opposite direction. Now, no matter what you do, there's always going to be some areas where there's just really no way to get around it. You will have sort of the positive sides of molecules near each other or negative sides of molecules near each other, but they will continue to sort of move and kind of adjust a little bit until they can find a livable arrangement of how they can interact with each other. So the first type of intermolecular force is dipole-dipole. It is really the type of interaction that occurs between one polar molecule and another. So this is sort of our polar and polar molecules interacting with each other. Or it's a polar molecule, just to be clear. So it could be two different polar molecules interacting with each other. It could also just be one polar molecule interacting with itself, right? So again, when you have some type of substance, it's not usually just one individual molecule in there, right? You usually have a ton of the same molecule in there, and they have to interact with each other. So, it's a way that they could interact with each other as well. Here's a much better picture, perhaps. And again, here on the right-hand side, that's what happens when we get a whole bunch of these polar molecules together. Again, they sort of do as much movement as they can. And the attractive forces, which is the red little lines, they try to really maximize that arrangement and kind of move around to, where the negative and negatives are sort of as far away as they can from each other. Positive and positives also sort of as far away from each other as possible. Now, another type of interaction that occurs is one that is referred to sometimes as ion-dipole forces. And ion-dipole forces are pretty much what the name sort of implies. It involves an ion, so that's either going to be a cation or an anion, right, or positive or negative guys. and a polar molecule. So this is again an ion and a polar molecule basically force. And this is essentially what happens when we take an ionic compound, for example, something like sodium chloride, which is a solid, and we dissolve it in water. So when we take something like sodium chloride and we dissolve it in water, the sodium chloride breaks apart into sodium ions and chloride ions, right? And in the presence of something like water, what happens is they each get basically surrounded by water, right? And the oxygen side of water will surround the positive guy. The negative side of the positive side of water, which is the hydrogen, will surround the negative guy. And basically it allows two things basically to occur. It allows the sodium chloride really to dissolve and sort of disappear in quotes, but it's not really disappearing. It just sort of went into the water network there. And it also prevents those two ions from coming back together. So without the water there, those two ions are going to be attracted to each other by electrostatic attraction. That's an intramolecular force, which is really super strong. So without those waters there, they're just going to want to cling back together, the positive and negative ion, and the solid would be reformed. And that's essentially what happens when you evaporate off the water. But by having these water molecules basically surrounded, it provides sort of a buffer that does not let that to happen. So basically what will happen is, again, the negative side of the polar molecule will be attracted to the positive cation, like we have on the bottom left there. If this is our cation down here, and this is our polar molecule, and this would be our anion on this side and our polar molecule over here. And again, we get that attraction between opposites attraction here. So the positive and negative being attracted to each other, and our negative and positive side of the molecule being attracted to each other. For equal sort of charges, as it says there, again, the cation will interact more strongly than the anion, and that's because, as you can see in sort of the picture, and as you hopefully remember as well, in order to become a cation or positively charged, you lost electrons, which means your overall size gets smaller, right? Because it lost a lot of those electrons in their electron cloud, and thus is a smaller molecule basically being grabbed on, or smaller ion being grabbed on by that negative side, as opposed to something that's a little bit bigger. Kind of like if you take a magnet and you try to grab something that's small, it'll come right onto the magnet. Try to pick up something that's a little bit bigger, right? You can still maybe do it, but it's not as hard. It's a little bit harder. It maybe doesn't hold as tight and stuff like that. So it's kind of a similar idea. Ionic compounds usually have a low solubility in nonpolar solvents. So if you remember when we talked about bonding, if something is nonpolar, it basically has no charge. So there's not a side that is positive, there's not a side that's negative. So when something that is an ion, like a positive or a negative ion floating around, it's like I have no way to interact with you, and they have really no long way to interact with each other. And that's why when we put an ionic compound into a nonpolar sort of solvent, they really don't mix very well, because over the long period of time, they have no way basically to sustain any type of meaningful interaction with each other. And that's different than when you put it in something like water, because water is a polar molecule. It has a fixed dipole, which will never go away no matter what the situation is. Water will always have a positive side and a negative side, and it always will have a way to interact with something that has a charge. So ion-dipole interactions is really that interaction that we see a lot when we dissolve some type of ionic compound in a solvent like water, for example. Now, let's talk about those non-polar guys and sort of how they interact. And they interact through a series of interactions which are known as dispersion forces. So dispersion forces are really how non-polar molecules interact with non-polar molecules usually. So that's usually dispersion force is sort of what we leave for non-polar. But, you know, there is a way you could sort of make an interaction occur, even if something normally doesn't have a charge. And that is what is sometimes referred to as an induced dipole. So an induced dipole is basically a separation of the positive and negative charge in a nonpolar or a neutral atom that's caused by the presence of an ion or a polar molecule. So even though technically speaking, a nonpolar molecule will not have a positive side or a negative side, you could kind of make it temporarily sort of have a positive side and a negative side. And so, for example, here we have our neutral atom over here, basically has no charge. If we roll up on it right now, something with a positive charge, right? And like an ion, for example, we put a positive ion next to this guy. So if we had our nonpolar guy here and we put a positive guy next to it, what's going to happen is all the electrons in this normally neutral guy will go, oh, cool, positive guy, I'm heading this way. So all the electrons are going to head over to the left-hand side in this example. And what's going to happen is that guy that normally does not have a charge will now temporarily gain a charge on that side because all the electrons really migrated over. And now this has a place where they can basically interact with each other. And that's what we see here. And that's what's known as an ion-induced dipole interaction, because it's the ion that's causing that temporary sort of attractive force, you know, between these guys. It's very weak in the sense that it's, you know, has to be induced. And it doesn't hold very long as well, because those electrons will, at some point, because they're moving around, want to head back the other way and stuff like that. And that sort of attraction will sort of break apart. So not a very strong sort of interaction that occurs. You could also do this by putting a polar molecule next to a non-polar guy. And that gives us what is sometimes referred to as a dipole-induced dipole. And basically the same effect occurs in that normally non-polar molecule. It will temporarily get this separation of charge, and that temporarily will give them a way to interact with each other through the positive side of one and the negative side of the other. So this is sort of, if you think about it, if you, like, for example, I don't know, like oil and vinegar salad dressing, for example, something like that, right? Temporarily, right, you can mix it up, right, and it will stay mixed for a little bit. And that's sort of these sort of dispersion forces that are sort of occurring here. They're able to kind of temporarily sort of mix with each other. But if you put the salad dressing sort of down, eventually what will happen is you'll get kind of two layers that will happen, right? They'll kind of separate out from each other. And there's kind of oil is nonpolar, sort of vinegar there is polar. So over the long period of time, they really don't have a good way to sort of interact with each other. But temporarily, they could sort of interact, but they won't be able to maintain that because, again, these electrons are going to be kind of moving around, and these sort of temporarily sort of attractions will sort of break apart. And that brings us to an idea which is known as, we sometimes don't even need a polar molecule or an ion to help us do that. Sometimes a nonpolar molecule, when it's around another nonpolar molecule, this is essentially how they're able to interact with each other, is their electrons themselves will kind of do that for them. And basically what we mean is if we have, say, two nonpolar molecules together, so unlike the last example where we had something with a charge, we have two nonpolar molecules. And if for some reason all the electrons in this guy decided to go vacation over here on this side of the molecule, because they're flying around, the guy on the left there, which normally would not have a charge, will now temporarily gain a charge where this side of the molecule is more negative because the electrons went that way, and this side is more positive. And now if he's still sitting next to this other nonpolar molecule, the electrons in the second guy is going to go, oh, my electrons don't want to be near you. The electrons in this guy is going to head over this direction. And what that's going to now do is in the second nonpolar molecule, create a situation where it also has now gained a temporary charge. And now these two guys that started out basically with no way to interact with each other have now gained sort of these temporary charges and also a way to interact with each other through the positive side and the negative side. And the ease at which those electrons could sort of move around is what is known as polarizability. And that's the ease at which electrons basically kind of go and end up at one side of the molecule or the other. And the ease at which you can do that gets greater with molar mass. So the greater the molar mass of, say, a nonpolar compound, the greater the chance that the electrons will kind of move around. And that's because when you have more molar mass, that usually means you have more elements. More elements means you have more electrons. More electrons there means there's a greater chance that some of those electrons are going to fly around and kind of end up on one side of the molecule versus the other. So this creates what we are talking about up here is what is known as an instantaneous dipole. And an instantaneous dipole is really the result of that, the electrons being able to be distorted and move to one side of the molecule versus another and create these temporary positive sides and negative sides in these nonpolar molecules, which normally do not have a positive or negative side. Now, they're temporary because as soon as some point, the electrons are going to decide, we'll go back this way. Vacation's over, summer's over, all those sad things. We'll go back that way. And obviously, it will then sort of go back to being nonpolar and break apart. But it will make some new ones, and those will be broken and make some new ones. So this type of interaction, these sort of dispersion forces in this sense, which creates these instantaneous dipoles, this again is really how these type of guys interact with each other. So again, that nonpolar interaction is really our dispersion forces, is where we definitely see that take a place. Any questions on that there? So these attractive forces arise in these temporary dipoles, which are known as dispersion forces. And as I mentioned, they do increase with molar mass. So sometimes you may be asked, hey, between these two nonpolar molecules, which one would you expect to have the higher boiling point? And although they are both nonpolar, for example, and they both will be using dispersion forces as their main root of intermolecular forces, the one that has the higher molar mass would have the higher boiling point, again, for this reason that we were just talking about, that it should have more electrons, again, a larger or greater chance that those electrons will be moving around. And as it also says there, obviously, the larger the molecule, the farther the way the electrons will be from the nucleus and not held as tightly and able to sort of move around. So dipole-dipole interactions, dipole-induced dipole, and dispersion forces. These are where sometimes referred to as van der Waals forces. And if you remember just a second ago, yesterday, we saw the van der Waals equation, right, for our real gases. And one of the main aspects of a real gas, as we talked about, is the interaction between gas molecules and gas molecules, the attractive forces and the repulsive forces. And that's what van der Waals did a lot of work on. And that's basically what we're talking about here, is that intermolecular forces, the attraction and repulsion type forces. And here's a prettier picture of, I guess, what I drew. So again, this sort of instantaneous dipole, this guy that normally doesn't have a charge gets this sort of temporary charge, going to create a temporary charge and another. And now we have a partially positive side on the left guy, partially negative side on the right. And again, they're able to now interact with each other. Now, the last sort of type of intermolecular force is what is known as hydrogen bonding. And hydrogen bonding is in reality a type of dipole-dipole interaction. And it's a special type of dipole-dipole interaction. It's actually a very strong interaction. And it is, as the name implies, hydrogen bonding. It is a bond between hydrogen and some type of electronegative atom like nitrogen, oxygen, and fluorine. And there's a reason for that. Is if you look at the periodic table, and if you look at where those guys are, we have nitrogen, oxygen, and fluorine. And if you remember about bonding that we talked about, as we head this way, the electronegativity, right, increases. And fluorine is our most electronegative atom you could have. And that's really important because when you have a hydrogen that is bound to a nitrogen, an oxygen, or a fluorine, what it's going to create is a separation of charge. So like when you have hydrogen and oxygen, the oxygen being more electronegative, being more negative on that side, more positive on that side. And again, that is the way something can interact with each other. And that's why when we look at water, and another water molecule, the positive, negative, right, for water is here, right? Hydrogen's being more positive. Oxygen's being more negative. And again, it's that opposite attract, the hydrogen here, coming here, and hydrogen bonding. And this is a really strong interaction that occurs, and that's why water, for example, has a higher boiling point. Now, in terms of our strengths here, are in terms of sort of the three major types of intermolecular forces are, hang on a sec, go this way. So we have dipole-dipole, and that really is for how a polar molecule and a polar molecule can interact. And these are typically the ones that cannot hydrogen bond. So typically dipole-dipole is for our guys that can have polar molecules but lack really the ability to the hydrogen bond. Our dispersion forces, as we've been talking about a second ago, are for our nonpolar and nonpolar guys, how they basically interact. And our hydrogen bonding here is for polar molecules and polar molecules that have the ability to hydrogen bond. So that's the sort of subtle difference between dipole-dipole and hydrogen bonding. Is in dipole-dipole, you may come across a molecule that does not have the ability to hydrogen bond, but that is still polar. and it will use dipole-dipole. While you could have a polar molecule that has the ability to hydrogen bond, and it will use hydrogen bonding as its major source of intermolecular forces. In terms of strength, the strongest out of all three of those is the hydrogen bonding. So hydrogen bonding is the strongest intermolecular force you could have. So number one, in terms of strength, number one is hydrogen bonding. Number two is dipole-dipole. And the weakest out of all of those is dispersion forces. And how does that relate to something like boiling point, for example? So how it typically relates to something like boiling point is if you're comparing two compounds or molecules, and one of those guys has the ability to hydrogen bond, while the other pretty much could only do dispersion forces. If you had a question where it said which one would have the higher boiling point, it would be the one that has the ability to hydrogen bond, because that hydrogen bond is a very strong intermolecular force, which means it's going to hold one molecule together with another one relatively strong. And that means it's going to take more energy to break it apart into its gas phase. So it would typically have a higher boiling point. The guy in dispersion forces is going to be using those temporary interactions that kind of come together, break apart, come together, break apart. And thus it will have a much lower boiling point. If you're comparing somebody that has the ability to hydrogen bond and somebody that could just do straight old dipole-dipole interaction, that too, the hydrogen bond would have the higher boiling point as well. So it is stronger. So you may ask yourself, what really is the difference between all three of these, in the sense that aren't they all essentially really just positive and negative attractions? And they are. All these things are really just ultimately positive side of one and negative side of another. But the major difference, especially when we talk about something like hydrogen bonding and dipole-dipole interaction versus dispersion forces, sort of the major difference between those two is in dispersion forces, it's temporary, which means those molecules normally, as they are kind of moving around, normally does not have a charge at all. There's no really positive side or negative side. They can temporarily gain these charges and allow them to interact with each other. But over really 100% of the time, they don't always have that positive side and negative side. And that is the major difference between that type of interaction and hydrogen bonding and dipole-dipole interaction. In both of those, the hydrogen bonding and dipole-dipole, there are polar molecules. And if a molecule is polar, basically what that means is 100% of the time, as they are moving around, there is a side that is fixed to be negative, and there's a side that's fixed to be positive. It will never kind of go away, that positive, negative side of the molecule. And because it has sort of that fixed side that's positive and that fixed side that's negative, that never goes away. That's why they are relatively stronger than dispersion forces, which are normally moving around not 100% of the time like this with no charge at all. They have to sort of gain those charges. So in terms of dipole-dipole and hydrogen bonding, because we have those polar molecules that have those fixed dipoles and those dipole moments, they're pretty much good to go 100% of the time to interact with each other, because they already have that positive negative side. That kind of nonpolar guy, he's got to kind of go, kind of develop it, if you will, the positive and negative side, and that makes it a much weaker interaction that's occurring when they try to interact with each other. Any questions on that there? So here's an example of some hydrogen bonding going on. So let's think about a few things and try to determine what we think would be the major intermolecular force. Would it be hydrogen bonding? Would it be dipole-dipole? Or would it be dispersion forces? So I'm going to give you a few molecules here, and you decide what type what is the major intermolecular force that should occur between these things? So let's see. Let's say we had, we'll do our water there. We'll do NH3. All right, take a few minutes here or a couple minutes here and think about each of these 3 or 4 or 5, whatever I put up there, different molecules, and try to decide which one of those 3 in terms of intermolecular forces would they use as their major part. So take a minute or so and then we'll talk about it. And by the way, while you're thinking about it, what we're sort of asking here is, for example, water interacting with itself. So how is water and water interacting with itself? How is NH3 and NH3 interacting with itself? You know, and so forth. Okay, so let's take a look and see. So first off, water. Again, sometimes we're not sure, perhaps just sketching it. Obviously, we've talked about waters enough in this example. But when we do draw water, water is polar, right? So it has a negative side and a positive side by the hydrogens. So it is a polar molecule. So usually when you get a polar molecule, what you want to decide is, does it have the ability to hydrogen bond? And obviously this is a hydrogen that's connected to an oxygen. So it does have the ability to hydrogen bond. So hydrogen bonding here would be the major type of intermolecular force that would happen in water, interacting, for example, with water, and probably how water interacts with a lot of other sort of guys as well. NH3, again, if you drew NH3, looks something like this. And if you remember, if you look at this, this is a unsymmetrical geometry. And everything's attached, which means this is also a polar molecule. So then you have to decide, does it have the ability to hydrogen bond? It does have a hydrogen, and it is connected to a nitrogen. So that pretty much checks both boxes there. So it also would use hydrogen bonding as its main source. So far we've seen a couple of things here with hydrogen, and having that ability to hydrogen bond. So why don't we'll go to this guy first. Let's take a look at CH4. Now, CH4 definitely has a ton of hydrogens, right? But when we think about CH4, hopefully you remember that the carbon-hydrogen bond is nonpolar, is like 0.4. And to second that, the geometry here is tetrahedral and everything's attached, which means it also is a nonpolar molecule, this guy. And because this is a nonpolar molecule, even though it has a ton of hydrogens there, the hydrogens are not attached to nitrogen, oxygen, or fluorine. It's attached to a carbon. Thus, that means this whole thing's nonpolar. And even though it has all those hydrogens, the best it could do is dispersion forces, which is basically the force that we use for nonpolar and nonpolar guys to come together. So again, that's a very good example that sometimes people see the hydrogen and go, oh, cool, it's got hydrogen, it's got a hydrogen bond. But it has to be a hydrogen, like in the first two examples, for example, there, that it's attached to either a nitrogen, oxygen, and fluorine. And the reason for that, again, is because when that hydrogen is attached to those three elements, it's going to create such a separation of charge that you are going to get a positive side and a negative side. But when it just goes one more over to carbon, we then get that nonpolar sort of bond that occurs, and all those hydrogens are sort of useless, if you will, in terms of hydrogen bonding. Now, what happens when we take CHF3, if we draw it really quick here, just kind of give a rough sketch of it, like something like this. So this is, as I drove it right into that guy there, let's just go this way. This is tetrahedral geometry, but we don't have everybody attached the same. So this is actually going to be a polar molecule because of that. All the electrons are going to head towards the fluorine because it's more electronegative. It doesn't have a hydrogen at all. It does actually. It does have a hydrogen here. But this hydrogen is not attached to a nitrogen, oxygen, or fluorine. So even though it is polar, this guy is not going to be able to do hydrogen bonding because this is a nonpolar bond. So it will use dipole-dipole in this case because that's the only thing that it has available to it for our polar guy. And lastly here we have N2, which again, if you kind of quickly sketch it, that's your triple bond, looks like that. It is a diatomic molecule. It has obviously the same element on each side, which means this guy is going to be nonpolar, which means that he is also going to use dispersion forces, right? Any questions on that? And just a note on that, if you are familiar with methane, which is the gas that comes out when you light your Bunsen burner, if you're familiar with nitrogen, which is also a gas, those two things are typically found in gas. As you can see, they are also the two things that have the weakest intermolecular force, which means they can kind of go into the gas phase relatively easy because of that, because they're only using dispersion forces to try to hold them together. Any questions on that? So a lot of times you'll get a question like this where they'll ask you again, sort of what is the dispersion force, and they just give you one molecule. And that basically is how, it will interact with itself. It also is usually how it can interact with something else. So for example, if we took water and we took something like methanol here, so something like this. This part of methanol has a positive side and a negative side because it has that HO. So these two different guys, when they come together, can hydrogen bond as well. So you can apply intermolecular forces to two different molecules, like the case here, water and methanol, hydrogen bonding, are with itself as well. Again, because this guy has this little bond here, it could do that hydrogen bonding. Any questions on intermolecular forces? So again, you need to know the three major types, which again are dispersion, dipole-dipole, and hydrogen bonding. And obviously, like a question we just sort of did there, be able to identify the major intermolecular force that would be used. So now we're going to kind of switch gears and just talk a little bit about sort of the liquid state. Liquids are much closer together than gas. So obviously in the gas phase, they are flying around, and that is what causes pressure and stuff like that, like we talked about with gases, the collisions. So in the liquid state, they are together a lot closer. There's a little bit more room for movement than you find in the solid state. That's why when we think about liquids, right, we think about them as being fluid. They have enough energy basically to sort of move past each other, the molecules in the liquid state. And again, that's what sort of gives liquids its characteristic fluidity. And you lose that when you get into the solid state in most cases, because in the solid state, they no longer have enough energy basically to pass one another. So they sort of stick together and, you know, can't move. And something known as viscosity is basically the resistance of a liquid to basically flow. Let me see your question. I'm not sure I understand your question. I'm sorry. I don't know what you mean by Riemann structures. You should know how to draw Lewis structures if that's what you're asking. We did that in an earlier chapter. So if you had to sketch them, you should know how to kind of draw those structures. And if it was something, you should be able to sort of figure out how to draw the Lewis structure if that's sort of what you're talking about. So from this slide, are you asking, do you need to know how to like draw these structures? Yeah, that's something you should know how to do. That's what we talked about with Lewis structures, how to draw those. And again, it would be, I don't know, you should know the name and how to draw the Lewis structure. I'm not sure what that is. Are you talking about these guys here? You don't have to draw these structures if that's what you're talking about. You do need to be able to do Lewis structures and stuff like that. No, those are what are referred to as space field structures. You don't have to do that. It's just a way to represent it. Yeah. So I would just say you just need to know how to draw Lewis structures like we talked about in terms of any type of structure. And that should be able, you should be able to, from that, determine the intermolecular forces. Okay, so talking about viscosity, you're welcome. So talking about viscosity is the resistance of liquid to flow. So guys, with it is related obviously to intermolecular forces. So sort of the stronger the intermolecular force, the weaker, the lower the viscosity will be, and sort of the higher viscosity will happen with sort of the weaker intermolecular force as they're able to kind of move around. And that brings us to sort of water and some important parts about water. And there's a couple type of forces that we will see. And it basically is what we see when we put something like water into a cylinder, like liquid, like a glass cylinder, like a graduated cylinder, or a burette, a pipette, any of those type of things. And these are what are known as cohesive forces and adhesive forces. And cohesive forces are the attractive forces between a molecule of a single substance. So it's the attractive forces between, say, a water molecule and itself. Its cohesive forces is how attracted they are to each other. Adhesive forces are the attraction between, say, two different molecules. And as we'll see in a later slide, this is really what creates that as you were told a lot, when you take a liquid reading in a glass tube, you look for the over-exaggeratedly drawn meniscus here, right? And it's that curvature of the liquid, and we usually read right from the bottom of the meniscus. And basically, as we will see a little bit later on as well in this chapter, is what causes that curving to occur is the adhesive forces, the attraction, say, between water and the glass, is stronger than the attractive forces between, say, water and itself. And what ends up happening is, because the adhesive forces are stronger, the water basically starts to climb up the sides of the wall. And it creates that curvature in that liquid that we call a meniscus. And that's basically what's happening in that case. And that means that the adhesive forces, again, the forces between the water and the glass in the container, is stronger than the cohesive forces, which is the forces between, say, water and itself. And that causes that sort of curvature to occur. Now, another sort of feature of water was referred to as the surface tension. And the surface tension is basically the tendency of basically the surface of a liquid to basically expand out and kind of stretch, if you will. And the idea there is, again, if you think about just water molecules, and we'll see maybe a better picture in just a sec, but water molecules or any type of liquid sort of at the surface, it really has attractive forces to the left, to the right, and down. And you can kind of imagine if you pull something from the sides and down, it's going to really stretch the surface of it. And it creates that surface tension up here, up on top, as it's doing that kind of side to side stretching and downward stretching. And that's different than what, say, water molecules under the surface basically feel. So under the surface, if we were looking at, say, a water molecule, this guy in the middle, he would feel attractive forces kind of all the way around him and sort of be stretched equally, if you will, as opposed to the guys at the top, they're missing that kind of guy above them to pull them up in the upwards direction. So they get basically stretched out. And energy is needed basically to expand that liquid surface. And the surface tension is higher in liquids that have greater intermolecular forces. So something like water, which has hydrogen bonding, which is a very strong intermolecular force, it's going to be pulled really tight to the left and down, and it's going to create that really, really tight surface tension. For example, you could lay a paper clip carefully on some still water, and it will kind of float there on the surface. And again, water has a very strong surface tension because of that hydrogen bonding that it's able to do, right? Kind of also similar to a couple other factors, but kind of similar to like if you ever poured, say, soda or liquid into, say, a cup or something like that, and at some point you look at it and go, wow, I'm kind of like over the top there. And then you sort of move your hand a little bit because you're looking at it, and you kind of break that surface tension, and then you make a mess. But, it's able to sort of maintain that. That's why certain sort of bugs, if you will, right, can walk on water, right, pretty easily because they have that surface tension and they're able to kind of go across it. Here's a, I don't know if better picture or not, but basically what we see is at the surface, we have a lot more stretching to the sides and down, again, creating that surface tension up here. And again, we don't have that in the middle because sort of, I don't want to say perfectly equal, but pretty much from all around, he's getting kind of pulled, if you will, and attracted, and it's not going to get so, for lack of a better word, distorted there and create that surface tension. And that's also why we use things like, for example, soap and so forth. Soap basically is two parts. Soap is, it has a nonpolar part, which is sometimes referred to as the tail. And in organic chemistry, these are all carbons and hydrogens I'm drawing. Kind of looks like a mountain range. These are all basically carbons and hydrogens attached. And at the end of soap is usually a polar part. So soap usually has this nonpolar part. And over here, it has a polar part, which is sometimes referred to as the polar head, and the nonpolar tail. And basically, when you put soap in, it interferes with this hydrogen bonding that occurs with our water, which is why when we go to wash our car, for example, are when water hits our car and so forth, or an umbrella or something that's been waxed like our car, water tends to bead, right? You see all those beadings that occur basically. And that's because it's basically interacting right with wax or that sort of non-polar things. So they're not going to interact very well with each other. So it tends to bead. But when we put our soap down, right, we wash our car, then put our soap, the soap molecules basically get in between the water molecules and basically interrupt that hydrogen bonding that occurs and allows the water basically to kind of spread out, right? Spreads out. And that's why, again, we typically will put water our car and then put some soap and water on it, right, to clean it, and allows really everything to kind of spread out. The good news about that as well is when you're doing the soap part is dirt is nonpolar. So the nonpolar side of soap will basically trap the dirt in it. And that's essentially how soap works. There's dirt, which is nonpolar. So that kind of nonpolar side of soap will basically be trapped in it, and that's known as a micelle. And the nice thing about that is when it traps it on the outside, we have the polar part of soap, and you typically will then wash off it with water, and that will mix really well with water. So as the soap goes out that has the dirt trapped in it, you are clean. That is how soap works, I guess. And again, it allows it to sort of basically spread out. It's good to know how that works, I suppose. And just to finish up here, again, as we sort of talked about a second ago, the adhesive and cohesive forces. This is what happens when we put any type of liquid into sort of a glass container. Something known as a capillary action. You could actually take a capillary tube, it's kind of closed on one side usually and open on the other, and you can actually use this sort of effect to draw up liquid into a tube through what's known as capillary action. Use a capillary tube, basically you put it in and basically the liquid will be drawn up because the adhesive forces are stronger than the cohesive forces, and it basically will suck the liquid up. Again, it's also why, as I had mentioned earlier there, that we see the meniscus, sort of that curvature of the water in a glass tube. Again, the attractive forces between the water and the container is stronger than the water in itself in this sense. Also why, if you ever have seen mercury in a tube, it actually does a inverse, I guess, meniscus, where you read from the top. And the reason for that is the opposite is actually true in that case. The cohesive forces, the forces of attraction between mercury and itself, is greater than the attractive force between mercury and the glass tube. So what ends up happening is all the mercury guys are attracted to themselves, and it causes the mercury actually to sort of contract down, as opposed to when the liquid is attracted to the walls, where it rises up it and creates that meniscus going in that direction. All right, any questions on that? So it's a good stopping place. We will stop here. Again, a reminder that we do have the exam today. Just like normal, you got to have your camera on, right? Your Chrome, your proctorial. Again, you should have out just a paper, a calculator, and something to write with. No other notes, cell phones, anything like that. Make sure all that is put away. And just like normal, it's going to be 2 parts to the exam, just like it was the last couple. There'll be a first part, which is a multiple choice part. You do not have to show work for that. You can just answer the questions. There will be a second part that is a written part. And again, some of those questions will require work to be shown. Like normal, if you want all the points for those problems, make sure you show all the work. And once you have submitted your exam, within like 10 minutes or so, you should submit your work and have it uploaded as well. The homework, as I put an announcement out as well, is officially due Monday. But if you're done with it and you want to turn it in, the box should have just opened, I think, about 5 minutes ago, so you can turn those in as well. There will also be, like normal, you'll have a conversion, yeah. So you'll have some conversions given to you, periodic table given to you. I think you also maybe have a solubility table if you need it. It will be there as well on there. So they should all be on there, I believe. I think every conversion that you would need should be there. If you don't see it, you probably don't need it, I would imagine, in most cases. Other questions on any of that? Okay. So a couple of other reminders. Remember that we're down to 2 weeks to go, 8 days. Yeah, so that's not too bad. So reminder, 1 week from today is exam 4. So we will be covering material, obviously, at the beginning part of the week that will be on there. So we have a lab report due as well for the titration is due on Tuesday. So again, make sure you keep up with all this stuff. A lot going on here in the last 2 weeks to finish out the class. So, you know, that is the unfortunate beauty of summer school. It goes quick, but then there's only so much time, right? So we have to do all this stuff anyways. All right, any questions on any of that stuff? All right. Other than that, it does. So as we talked about the last couple of days, it stops at partial pressures in your notes. I think I went back and sort of put a line there. So everything in terms of the gas was up through partial pressures. So none of the stuff that we talked about yesterday in terms of whatever it was, root mean square and diffusion and all that kind of stuff. Yes, the solubility rules are given if you need them. All right, any other questions? All right, other than that, make sure you put here if you haven't done so. Have a very good weekend. Remember, there's no lab. Obviously, we're going to use that time to take the exam. And next week, we will be off to, I think, the gas labs. We'll start those, I think, on Monday. And we'll continue lecturing on this. After this, we are down to 2 chapters, I think, to go as well. So we're getting to the end. All right, good luck on your exam. If you have any questions, you could email me through Canvas, but I think it should be pretty self-explanatory. Have a good weekend, and I will see you on Monday.